CIIS has provided a significant platform for collaboration, research sharing, and advancement in internal combustion engine and combustion sciences. Hosting ICICEPC 1.0 here at Graphic Era, deemed to be university, reflects the institution's commitment to innovation and excellence, founded in 1993 by Professor Dr. Kamal Ghanshala, with a vision of transforming education in Doon Valley. Graphic Era has grown remarkably. Starting as the Graphic Era Institute of Technology in 1996, it attained deemed university status in 2008. Today, Graphic Era is a NAAC A+ accredited institution with 7 NBA accredited programs and ranks among India's top 100 universities as recognized by the International Institutional Ranking Framework. With a robust focus on industry-academia partnership, Graphic Era collaborates with industry leaders like Tata Technologies and IBM and promotes entrepreneurship through the Technology Business Incubator. Through global partnership and a strong alumni presence in the top organizations like Apple, Google, and Microsoft, Graphic Era continues to make an international impact. This conference serves as a vital platform for discussing advancement in internal combustion engine, propulsion, and combustion technologies. It fosters collaboration, knowledge sharing, and innovative solutions to the challenges in our field. As we proceed, it's our privilege to welcome 3 distinguished speakers whose groundbreaking work inspired the shape of our field. With great enthusiasm, we present 3 eminent individuals bringing knowledge, vision, and inspiration to this conference. First, I would like to introduce Dr. Zhang. It's a pleasure to invite Dr. Zhang to this conference. Dr. Zhang has received his bachelor's degree in engineering mechanics and master's degree in fluid mechanics in 2007 and 2009, respectively, from the School of Aeronautic Science and Engineering, Beihang University. He worked as a full-time research associate in the State Key Laboratory of Turbulence and Complex Systems, Peking University from 2009 to 2011. He obtained his PhD degree in Energy and Combustion from the Department of Engineering, University of Cambridge in 2015. He then stayed on in the University of Cambridge to take up a postdoctoral research associate position on pulverized coal combustion. His research field are combustion and reaction flow, turbulence, combustion modeling, multi-phase combustion, near-limit flame dynamic, high-performance computing of reacting flows, and parallel algorithm development. He was awarded the Professor Qin Zing He Memorial Scholarship, Professor Alan T. Chuang Fluid Mechanics Scholarship, Excellent Graduate Student of Beijing City, Cambridge Overseas Trust Scholarship, Dorothy Hodgkin Postgraduate Award, and received the Postdoctoral Research Fellow from the Center of Turbulence Research at Stanford University. He is also selected by the UK Pilot Center Europe Research Committee on Flow, Turbulence and Combustion as a finalist for the Osborne Reynolds Research Student Award due to the excellence of his PhD research. He is the reviewer for many journals like Flame, Proceedings of the Combustion Institute, Combustion Science and Technology, Fuel, Energy and Fuels, Microgravity, Science and Technology, etc. Please join me in welcoming Dr. Zhang. Professor, can we start with the presentation?
Good morning, everyone. This is Zhang Huangwei from the National University of Singapore. So, firstly, I would like to thank Professor Randy and Dave to invite me to give this talk. I will be presenting the extinction and flammability limit of ammonia hydrogen blends under engineering conditions. So this work mainly from my PhD student in NUS and this work is sponsored by the Taiwan Research Program funded by National Research Foundation in Singapore. So parts. The first one is the introduction, and then I will introduce the numerical method we use for this work. And in the results and discussion part, I will cover two problems. The first one is the adiabatic stretched ammonia hydrogen blend based on the current flow configuration. And the second one, we will further examine the effects of the radiation on the extinction and flammability limits of hydrogen flame, or hydrogen and ammonia flame. The conclusion will be covered in the first parts, and if we still have time, I will introduce the Asia-Pacific Conference on Combustion, which will be held in Singapore next May. So here you can see the increase of the CO2 emissions since the last century. Okay, so we can see actually the CO2 emission is mainly from the fossil fuel combustion. So in terms of the greenhouse gas emissions, CO2 also accounts for the around 65%. So basically, CO2 stands out as an important greenhouse gas, which drives the global warming. So global warming actually will lead to increase the frequency and intensity of the heat waves and extreme weather events. So here you can see an example from the Indonesia, which is the forest wildfire. So you can also melt the glacier, okay, and which may raise the rising sea levels. Okay, so here is an animation to show the changes of the sea level around the Singapore. So it is very important for us to tackle the global warming, so we can decarbonize the energy sector. Okay. So in 2022, Singapore published the National Hydrogen Strategy. So in this document, the technical strategy and the different technology routes and also the outlook are given, okay, for this country. So low carbon energy has the potential to be the major decarbonization path to support Singapore's accelerated transition towards net zero, okay, by 2050. So here, in this document, the applications of hydrogen and ammonia for power is mentioned. So here we can look at this schematic. Since Singapore actually is an island country, so the ammonia is imported from overseas sources. Okay, and then it is unloaded from the tankers at the piper. Then for the end users, actually we can see different. We can see two end users. Okay, so this is actually ammonia is directly used for power generation as a fuel. So another way actually it is to first crack to release the hydrogen. Okay, so this process actually is expected to be a land and energy intensive. Okay, so finally at the end we use the hydrogen. Okay, so for decarbonization R&D in Singapore, one of the very important program under NRF, it is so-called low carbon energy research program. Okay, so we have two phases now. For phase 1, we already have 12 projects, which started in 2021, around 3 years ago. Okay, so in this actually here we have the hydrogen production projects and also the carbon capture utilization and the storage projects. And at that time, actually, ammonia project is still limited. There's only one ammonia cracking project. Okay. However, in the second phase, which starts early this year, so there are around 16 projects. So there are two categories of the projects. The first one is the direct hydrogen program. So for this category, it aims to build a capability across hydrogen supply chain and end users, such as the combustion. Okay, and then the second category includes the emerging technology. Okay, so this actually is to develop nothing yet promising low carbon energy technology. Okay, so this is the high TRL project, and this targets the low TRL. Okay, so in these 16 projects, there are 6 ammonia-related projects encompassing ammonia transportation, cracking, and also utilization. Ammonia as a fuel, actually, I think it is widely studied in recent years. So basically, we have the blue ammonia. If it is derived from the fossil fuel, We can also have the green ammonia, which is more promising if it is from the renewable energy. Okay. And then for the downstream application, it can be used like fossil fuel, industry furnace, and also power plants, and the marine fuel, and for automotive fuel. Okay. So it has some advantages. So first of all, of course, it is carbon free. Okay, so there is no greenhouse emission after it is burned, and we also have the possibility to have the green or blue synthesis if it is from the solar or electricity, and it also has a superior energy density. Okay, and we can also leverage the existing infrastructure and so the lower economic cost. However, it also has some challenges. Okay, so the first one, it is a very high minimal ignition energy, so it is very difficult, to ignite and easy to quench. So basically, here you can see, we calculate the different fuels: ammonia, hydrogen, and methane. So the minimum ignition energy for ammonia, it is around 8 millijoule. However, for hydrogen, it is much lower. Okay. The second point is a low burning intensity. Okay, so you see ammonia, it is around 0.07 meter per second, and for hydrogen, it is 3.5 meter per second. Okay, and the last one is about emissions. We have the nitrogen pollutant emissions from ammonia combustion, so we need to develop scrubbing system, okay, if you'd like to use ammonia in the engine. So there are different ways actually to enhance the ammonia combustion. One of them is the fuel blends. Okay, so if we blend ammonia with hydrogen, so it can significantly enhance the reactivity. So here we can look at the minimum ignition energy as a function of the equivalence ratio. So this one, it is pure ammonia, okay, 100 ammonia, and then we have some hydrogen blend. This is 10% hydrogen blend increased to 70%, and this is pure hydrogen. Okay, so we can see actually the minimum ignition energy is reduced significantly as long as we have the hydrogen addition in the fuel mixture. Okay, basically same for the laminar burning velocity. Okay, we can see if we increase the hydrogen fraction, the laminar burning velocity increase very quickly. Okay. So for the hydrogen and ammonia combustion, this table actually summarize the different experimental results. Okay, focusing on the speciation and ignition delay and laminar burning velocity. Okay, so you can see actually here they are measured from different facilities, including shock tube, flow reactor, jet stirred reactor, and also some constant volume vessel. So the conditions are also listed here, including temperature, pressure, equivalence ratio, and so on. So what are the conditions for the internal combustion engine? So this actually shows the pressure versus the temperature. Basically, for internal combustion engine, it is around here. It is around here. So corresponds to the relatively high pressure and intermediate temperature. Okay. So if we look at this data again, we will find that actually relatively limited data actually corresponds to the engine conditions. Okay, so the pressure here, I highlighted here, this one is relatively high, and this data actually the pressure is relatively high, and then for the rest actually it is much lower, okay, than the engine conditions. So this figure we further visualize actually the operating condition in this test. So basically you can see for the studies on the ammonia hydrogen combustion on the low, intermediate temperature and the high pressure condition are still very limited. So so here we would like to show you one example about the ammonia and hydrogen combustion at the low temperature and high pressure conditions. So this is from the RCM. It is from the work done by Liao and published in CNF. Okay, So this actually is the chamber pressure versus the time history of chamber pressure. So we can observe two-stage ignition. Okay, so this is the first stage. This is the first stage. Okay, and after a period, and then we can observe the second one. So this actually is novel. Okay, so we for this is actually the time evolution of the species. So for the first stage, only the hydrogen is fully consumed. Okay, here it is very close to zero, and the major products here are nitrogen, N2O, and H2O. Okay, so for the second stage, so it is around here. The ammonia is fully consumed. Okay, and at the same time, N2O is converted to NO of nitrogen. So this actually is a very novel observation. Okay, so we would like to say, if this low temperature hydrogen ammonia blend combustion at elevated pressure is caused by the low temperature chemistry. So when we say low temperature chemistry, it is extensively studied for the hydrocarbon fuels. Okay, so you can see here, this is the current flow flame. Okay, so for mixtures actually with low temperature chemistry, normally we can observe a cool flame. Okay, it is a cool flame. Cool flame it is very useful for studies of the chemical kinetics. Okay, it is served as a crucial benchmark. Okay, for us to understand and validating the low temperature chemistry. Okay, so this is the temperature versus the strain rate, and this is the adiabatic condition, and this is the relation is considered. So basically, we can observe the hot flame and the warm flame and also the cool flame. So basically, the extinction strain rate and the flammability limits of the cool flame can be larger than the hot flame. Okay, so this is the extinction. This is the cool flame. Okay, extinction limit. Okay, so this is the hot flame extinction limit. So basically, you can see the cool flame extending the strain rate here. Okay, extend the strain. And given some suitable condition, this cool flame may also affect the flame dynamics. Okay, flame dynamics. So for the flammability limits, okay, you can see here. So when we change, the O2 mole fraction, so the flame curve actually will become smaller and smaller. Okay, so once this curve actually is degraded to 1 point, so this hot flame become inflammable. However, for the cool flame, actually, it is still, we can still observe the flame solutions. Okay, so basically, we can see, the cool flame may extend the flame limit. Okay, so for the hydrocarbon fuels and for the ammonia and hydrogen fuel blends, recently we also have some results from the literature. Okay, so this actually is a work just from the symposium this year. Okay, so this is the maximum temperature as a stretch rate, and this is the extinction stretch rate as equivalence ratio. Basically, we can see when we change the equivalence ratio. Okay, so the flame will become flammable stretch rate range become narrow and narrow. Okay, so it's essentially it will close to the limit. Okay, if we further reduce the equivalence ratio to less than 0.6. Okay, and for this case, actually they consider different pressures. So here it is 1 atm, and this one it is 5 atm. Okay, this is based on the premix, the control flame, and another work it is from. It is based on the constant volume cycle flame. So here they tested actually different initial conditions, and this is the lower flammability limit as a function of the hydrogen content. So basically we can see, if we increase the hydrogen content, the LFL decreases very quickly. Okay, they test different pressures. However, for most of these studies, actually it is below 5 atm. So basically, we still don't understand actually how the ammonia and hydrogen the flammability limit changes with the fuel properties. Okay. So in this work, we will consider the premixed counterflow flame to study the existence and application of the weak burning flame for hydrogen and ammonia mixtures due to a low temperature chemistry. And we will also reveal the weak flame structures and the underlying low temperature chemical pathways for both ammonia and hydrogen. We will also explore the operating conditions for the weak flames, and we will see actually how these weak flames will affect the extinction limit. So in the second part, we will consider the radiation effect. So we will try to investigate the radiation effects on flame applications and examine ammonia oxidation routes and near limit flame conditions. And we will also try to understand the influence of hydrogen condition, hydrogen addition and pressure on the flammability limits and the role of the low temperature chemistry. So the second part is about the numerical method. So here we will consider the pre-premixed counterflow flame. Okay, so this is the inlet, this is the ports. Okay, so here we will have the ammonia, hydrogen, and air injection. Okay, and this is another port, and this is the symmetric plane. Okay, so basically we will have two flames here. So the distance between these two ports is 40 millimeter. So this is fixed in our simulation, and this configuration can be parameterized by the stream rate AG. AG is defined like this way. Okay, it is related to the inlet velocity and also this distance. Okay. So we solve this problem using Cantora with specialized arc length continuation method, and we consider the chemistry. So we use the mixture average model. Okay, but we neglect the solid diffusion. And this is the governing equations. Okay, so here we highlight the radiation term for the energy equation. So here we consider, in the second part of this work, we consider the radiation, and we use the optical AC radiation model, and incorporating four radiative species: ammonia, H2O, NO, and N2O. So for the gas-phase chemistry, we examine this Liao 2023. So with 38 species. Okay. So this we did some validations for this model. Okay. So the first part is the laminar flame speed, and you can see SL, the laminar flame speed, actually we can reasonably well reproduce SL for different pressures from 1 atm to 5 atm. Okay, and this is for the ammonia hydrogen fuel blends. Okay, with hydrogen mole fraction of 0.4. So basically, we can also reasonably produce the SL for a range of the equivalent solution. So this is some comparisons about the flow reactor speciation profiles. Okay, and consider different hydrogen fractions from 100% hydrogen to 0% hydrogen. Okay, so I would say actually overall, this mechanism can reasonably reproduce this species profiles. Okay. So the last one is the RCM data. So here we compare the ignition during time for different pressures. Okay, for different pressures. So this mechanism is suitable for the current operating conditions in this book. Okay, in terms of the laminar burning velocity and also the speciation profiles. Okay, so then in the results and discussion part, I will first show you the adiabatic hydrogen, ammonia hydrogen counterflow flame. Okay, so this part of the work has been published in combustion flame. So this is the results. Okay, so this is the maximum temperature, and this is the stream rate. Okay, so here we show the flame solutions with different temperatures. from 300 Kelvin to 700 Kelvin. Okay, so the equivalence ratio highlighted in yellow corresponds to the normal hot flame. Okay, so this flame has a high temperature and also high heat release rate. Okay, and so for all these cases, actually we can observe the cool flame. Okay, so regardless of the choice of the temperature. Okay, so we can compare the flame structure for the hot flame and cool flame. So we choose the 500 Kelvin case, okay, for this black curve, and if we look at the AG, the weak flame actually corresponds to the dashed line. Okay, the hot flame is a solid line. So basically, we can see the weak flame, the heat release rate of the weak flame is much lower, okay, than the hot flame. Okay, than the hot flame. So we can further compare, the radicals. Okay, so this figure, the right figure, actually, we show you the normal hot flame and the weak flame. This is the species. This is the profiles of the different species. Okay, so what we can see here, it is the normal hot flame. Actually, the flame thickness, it is around the. They are also present in the hot flame, such as HO2, H2NO, HONO, HMO. Okay, and so for the OH radical, it is present in the weak flame, but actually, the quantity it is very small. Okay, it is very small, as you can see from here. 60. Okay, and the deactivated reactions are 0, I4, and 61. Okay, so as you can see from here, this is actually the heat release rate for the normal hot flame and also the weak flame. Okay, so for the hot flame, the 160 contributes by log for the heat release. Okay, and then the next one it is 61. Okay, so 61 and 160, they are ammonium reactions with OH radical. Okay, and here it is amine radical reacts with OH. Okay, for heat absorption. Okay, so these two actually are the endothermic reactions. So this corresponds to R0. So H react with O2 to have O and OH, and the other one it is for R4. Okay, so we have OH plus OH to have H2 and O. Okay, so this for hot flame, and for the weak flame is still the 160. So ammonia reacts with OH to have H2 and H2. Okay. So here we further look at the reaction paths. So this the red one we start from. For the hot flame, we can see ammonia and NH2, and then we have two paths. One, actually, they have different paths towards hydrogen, towards nitrogen. So NH, okay, and NO directly to NH, okay, and there actually here there are also some reactions involved in the weak flame, okay, generating N2O, okay, N2O. So here we calculated the reaction path, okay, normalized by the reaction flux of this one, okay, of this reaction. So we actually show. So the circle means that we have two stable branches, including the hot flame and non. Okay, in this case. And we can further calculate, the two extinction, to strain rate under the limited. See here, actually, if we further increase the hydrogen, the existing range of existing operating conditions of the weak flame, okay, for different hydrogen mole fractions and equivalence ratios. Okay, so for the second part, it is about the radiation effect in the ammonia and hydrogen flames. So this one is the latest work in our group, and we just submitted to combustion flame for publication. So here we identify and the weak flame, and we will also do the kinetic analysis, okay, particularly when the radiation is present. And we will try to understand actually, 0.6, okay, so we can see, the weak flame, it is, the temperature becomes much lower, okay, it is even lower than 1200, okay. And the lower figure actually shows us, the results, when we further reduce the Equivalence ratio from 0.6 to 0.3, okay. So we can see, once the Equivalence ratio is reduced to very low values, such as 0.3, the curve actually becomes closed, okay. So now actually we only have two limit strain rate, okay. So this actually is it is extinction strain rate caused by stretch rate, and this actually is caused by the radiation, okay. So if we further reduce, so this closed curve will degrade to a point and which corresponds to the flammability limit, okay. So this for the lean case, and then for the rich case, we can observe the same. So if we increase phi to a relatively high value, okay, let's say 2.5, okay, the curve here actually is become closed, okay. So if we further increase, and we will have the we will reach the flammability limit position, okay. So this is the, and we also have the extinction limit. So this extinction limit indicates the jump limit, okay, for the weak flame comes to the lower flammability limit and the upper flammability limit, okay. So we are interested in the near. So one interesting phenomenon I would like to highlight here is the case of phi equals 3.4. As you can see here, we will have two closed circles here. So this one corresponds to a hot flame, and this one corresponds to a weak flame, okay, weak flame. So like for this case, actually, the hot flame, the strain rate actually to sustain the hot flame actually is already very limited, okay. So indicating actually it is very close to the flammability limit, okay. However, for the weak flame, the strain rate is still much larger, okay, than this case. So this actually means the existence of the full flame can extend actually the existence of the weak flame can extend the flammability of the ammonia and hydrogen mixtures. So we also show here the limit strain rates, okay, including the AGEXT-STR, and also the blue curve. The blue curve is the AGSTR stretch for the weak flame, okay, and the extinction limit, okay, and this actually is another extinction limit, okay, for the right branch, okay, for the right branch. Here, these are the chemistry. Actually, we did the similar analysis as I showed in the previous slides. Okay, previous slides. So basically, from here we can see, the conclusions actually are similar. Okay, so the H2O actually is dominant, and then the other, important reactions, including, the N2HX reactions. Okay. This figure is the relatively important figure actually, for the second part of the work. So this is the Equivalence ratio, okay, and this is the hydrogen mole fraction. So we show you here the rich flammability limit in figure A and the lean flammability limit in figure B. So if we look at the black curve, okay, so in between, okay, so this actually it is the flammable range, okay, flammable range in terms of the Equivalence ratio. So what we can see from this figure is when the hydrogen mole fraction increases, okay, the flammability range widens, okay. So if we increase the pressure, such as from 5 atm to 10 atm to 25 atm, this increased pressure also broadens the lean and the rich flammability limits, okay. And as the pressure increases, the higher hydrogen content is needed to initiate the low temperature chemistry. So here we highlighted the range of the existence of the the importance of the low temperature chemistry. Okay, so mainly the H2MO plus. Okay, so and you can see actually for the rich side and for the lean side, the H2MO plus actually they are important for both actually situations. Okay, so once this H2MO plus is activated, it significantly expands the flammability limit. So if we look at this black curve, so start from this point actually the H2MO plus it becomes important, and here the range of this flammable conditions actually is extended, okay, compared to this condition and this condition. Okay, so we would like to move to the conclusions. Okay, so in this work we started the twin premixed chemical flame with ammonia and hydrogen as a flame. Okay, so we observe a stable weak flame and due to the low temperature chemistry. Okay, and the chemistry, the corresponding low temperature chemistry of ammonia is identified. So it is ammonia to NH2 to H2NO, and finally to N2O and hydrogen. So N2O actually plays a very important role in this low temperature chemistry of ammonia and hydrogen plants. And we also identified operating conditions on which the weak flame exists. Okay, consider different hydrogen mole fraction, equilibrium ratio, and pressures. And the effects of the reduction on flame applications are examined for both ammonia air and ammonia hydrogen air mixtures. Okay, so through there actually we can observe very complicated flame applications. So we also plotted the regime diagrams to summarize the sustainable strain rate ranges of this weak flame and the normal flame from ammonia air, ammonia hydrogen air mixtures. Okay. And we also do the parametric studies, okay, to combine, to study the effects of the pressure and hydrogen addition on the flammability limit. Okay, okay, so that's all. Okay, and lastly, I would like to use maybe 1 or 2 minutes to introduce the Asia-Pacific Conference on Combustion. Okay. So ASCAP 2025 actually the theme is to build a zero carbon sustainable future. So it aims to advance research on decarbonization and promote sustainable combustion technology and foster international collaboration to address the challenges of climate change.
Thank you, Dr. Zhang, for the presentation and insight. If anybody has any questions from the participants.
Thanks for your nice presentation. I just have one clarification. You mentioned about the values of the laminar burning velocity. For hydrogen, you said it is 3.51 meter per second, and for ammonia, it is 0.07 meters per second. Okay, and most of the hydrocarbons are around ammonia. The values are around ammonia, though ammonia is not having any carbon atom. What is the reason behind that?
Sir, are we audible?
Okay, so thank you very much for your question. You mean the laminar burning velocity of the weak flame, right? If not, didn't get your question very clearly.
May I repeat the question again?
Yeah, maybe could you repeat your question again?
Okay. So for laminar burning velocity values you have noted down, in that ammonia is having a value of 0.07 meter per second and hydrogen 3.51 meters per second, and most of the hydrocarbons are around ammonia, maybe around 0.06 of that order. Why it is so, though ammonia is not having carbon atom? I would expect that it is somewhere close to hydrogen. What is the defect? Is it possible to tell me?
So basically, the laminar burning speed of the wick flame it is lower than the hot flame. This because actually overall, the reactivity of the wick flame is much lower than the hot flame. I think this may be the reason. I'm not sure I answer your question or not.
Do we have any other questions? So, Dr. Zhang, we don't have any more questions. Thank you so much for your presentation.
Okay, thank you very much. Thank you for your invitation.
Thank you so much. So next we have Dr. Ming-Hsun Wu. Am I audible, Dr. Min?
Hello, can you hear me?
Yeah, Doctor, we can hear you now. Am I audible to you?
Yeah, so I will start sharing my slide.
Yes. So Dr. Ming-Hsun Wu is an associate professor of mechanical engineering at National Cheng Kung University in Taiwan. He joined the department in 2007 after earning his PhD from the Pennsylvania State University. He received his bachelor's in mechanical engineering and master's in applied mechanics from National Taiwan University in 1997 and 2001 respectively. Dr. Wu's current research interest includes micropropulsion, oxy-fuel combustion, deflagration to detonation, that's DDT, and nanothermites. His paper on flame acceleration and DDT in microtube received a Distinguished Paper Award at the 31st International Combustion Symposium in 2008. He is also a recipient of the Bernard Lewis Fellowship from the Combustion Institute in 2010. From 2011 to 2016, he led two successive national energy projects of Ministry of Science and Technology Taiwan to commission the first 100 kilowatt industrial pilot scale oxy combustion research facility in Taiwan. He has also been the principal investigator for more than 20 funded research projects since 2010. Dr. Wu has supervised over 15 master's theses since 2007, several papers co-authored with his students and received award in national conferences. He is serving as a reviewer for more than a dozen international journals and is an editor for Combustion Quarterly Monthly Journal of Thai Power Engineering. Dr. Wu has also served as board member of Institution for Dynamics of Explosion and Retractive Systems and the Combustion Institute of Republic of China, Taiwan. We are privileged to have him with us today. Please join me in welcoming Dr. Ming. So can we start with the presentation?
Okay, thank you. Let me start with sharing again. So do you see the slide sharing right?
Yes, we can see it, sir.
Okay. So good morning to you over there in India, and actually I should say good afternoon here in Taiwan. Thank you for having me here to share some of our latest research achievement on green propulsion technology. And has been introduced by the chair. I'm Ming-Hsun Wu, and I'm working in the Department of Mechanical Engineering at National Cheng Kung University, Taiwan. So, to start, I would like to give a bit of background on Taiwan and my university, in case you are not familiar with us. National Chengkung University or NCKU Taiwan, Taiwan is an island in East Asia situated between Japan and the Philippines. My university, NCKU, is located in Tainan, the southern historic city. The university was established in 1931 and is currently one of the leading comprehensive universities on the island. Interestingly, although the Google map shows that it takes around 20 hours to travel from here to the conference venue in India, we are not actually that far away, far apart. We are actually just 2.5 hours apart. So, two time zones. And as for my background, I guess the chair has a very comprehensive introduction already, so I'm not going to go through it. But what I would like to mention here is that in the past 15 years, I've been working on a variety of research and educational projects, including clean combustion, green and novel propellants, waste energy recovery, as well as energy education. So here actually showcase a couple of different things we've been doing or currently working on. And these works include the real limit detonation, nanoenergetics, high pressure spray combustion, among others. And I would like to highlight a few unique facilities we have built at the university. For instance, we have several industrial pilot scale furnaces that allow us to test various combustion concepts using gas, liquid, and solid fuels. And I guess this kind of large-scale facility is not just pretty rare in Taiwan, also worldwide, especially in academic institutions. So using these facilities, we achieved Taiwan's first demonstration of recirculated flue gas-based oxy-fuel combustion. Additionally, we operate the country's first, actually design and commission the first critical carbon dioxide ranking cycle power generator, which is able to use for waste heat recovery. And currently, we are working on developing the high pressure spray combustion test rig, which will allow us to test gas turbine combustors. If you are interested in any of these topics, we welcome collaborations. So now, let's dive back to our topic today, green propulsion technologies. To start, we will look at why green propellants are essential for space propulsion, while traditional propellants like hydrogen have been effective, as you may know, but they come with significant safety and environmental concerns. That's why we are exploring new generations or a new generation of liquid monopropellants. In particularly for our team, we are very interested in hydrosol ammonium nitrate-based propellants, HAN for short. And my talk today will actually focus on our development of HAN-related technologies. These new propellants offer the potential of better performance and, most importantly, much lower toxicity, which is what makes it green. We will start by discussing how we synthesize propellant-grade HAN solutions, which is essential groundwork for our research. From there, we will explore innovative decomposition techniques like thermocatalytic decomposition using a new high-temperature catalyst, which is called hexoaluminate. And we are also developing electrolytic decomposition approach, which you can completely avoid the need of catalysts. And for hexoaluminates, it is, as I mentioned, a group of high-temperature catalysts, and we believe that it is able to address the challenge of HAN's higher reaction temperature. The electrolytic method, on the other hand, simplify things by removing the need for a catalyst bed in the thruster, as I just mentioned. Another challenge with HAN-based propellant is the burn rate spike caused by water boiling within the propellant. And we have tackled this by gelling propellant with fumed silicon. Building on this, we are now developing systems, propulsion systems. There's actually some ongoing work. So this is basically what I would like to discuss today in this talk. So first, as we consider the rise of space exploration in the past 10-20 years, apparently, this space propulsion has a growing role in scientific and commercial applications. The need of sustainable, safer propellant become even more apparent. Traditionally, space missions have relied heavily on chemical propellants such as hydrogen, which is known for its high performance and reliability. However, hydrogen also has significant drawbacks such as high toxicity and volatility, which make it dangerous to handle and store. Here in these pictures, you can see just how hazardous hydrogen is. To handle the propellant, full personal protective equipment as well as isolated working zone are essential. So since the early 2000s, there have been discussions about banning hydrogen due to its toxicity and environmental impact. I mean to mitigate the risk of handling exposure. But as you may know, hydrogen remains widely used in space propulsion today because no alternative have fully matched its reliability and performance. Potential substitutes including hydrogen peroxide, ammonia dinitride, and hydrosol ammonium nitride show promise but require further development. More research is essential to advance this new generation of propellants to find safer, effective replacement for hydrogen that meet the demands of the space industry today. So, green propellants are designed to offer reduced toxicity and a safer handling profile while maintaining comparable propulsion performance. Material toxicity is often measured by what we call LD50, which refers to the amount of substance that when administered to a mouse causes a 50% fatality rate. And shown in the chart on your right, hydrogen has an LD50 as low as 60 milligrams per kilogram of body weight, meaning just 60 milligrams per kilogram can result in a 50% fatality rate. But even as you know, even skin contact with hydrogen can be deadly with an LD50 of just 91 milligrams per kilogram. In comparison, green propellants like Han-based SHP 163 and AFM 315E have overall LD50 values above 500 milligrams per kilogram. And the other type of green propellant, hydrogen peroxide, its LD50 is even higher. Just to put this into perspective, common substances like table salt, LCl, can also be fatal if consumed in excess amounts. Green propellants are not only less toxic but also exhibit lower vapor pressure and reduce environmental risk. Another major benefit is storability. Traditional hydrogen propellant require careful storage to prevent degradation, whereas Han solutions are relatively stable under atmospheric conditions. The focus on storability is crucial, especially we consider longer missions where fuel stability over time can make a significant difference in mission success. Among the green propellant, Han and ABN-based propellant offer better storability compared to hydrogen peroxide, which has a chemical potential for self-decomposition. In fact, green propellants are designed to avoid the need for complex, hazardous handling procedures, which is advantageous for both ground crew safety and reducing operation costs. So, this slide shows the chemical structure of the three promising green liquid monopropellants we just discussed. Both AN and ADN are classified as what we call ionic liquid, meaning they are made out of an anion and a cation, which they can be solid in very pure form. They are typically stored as aqueous solution due to their high hygroscopic nature, which make them easier to handle. These propellants are oxygen-rich, both quite stable under normal atmospheric conditions. On the other hand, hydrogen peroxide, referred as high-haze peroxide or HTP, when concentrated above 85%, it is highly oxygen-rich, and to use it in catalytic decomposition, the stabilizer must first be removed, what can make handling a bit challenging due to its reactivity. And also due to its highly oxygen-rich, it's impossible to blend it with another fuel to make it more stoichiometric. But for AN and ADN base, due to its stability, typically, since it is oxygen-rich, they are blended with a fuel and a performance modifier to create an effective propellant. The table here shows the composition of several AN and ADN-based propellant blends. Most of these are in aqueous solution form, and we will discuss later, the presence of water can actually lead to some undesirable burning characteristics. But at the end of the day, the key characteristic of any propellant is its propulsion performance. Specific impulse, often abbreviated as ISP, is an important measure of how efficient a propellant can produce thrust. Here, we are comparing the ideal specific impulse and adiabatic blend temperature of these propellants. As we can see, the green symbols represent ISP, and on the leftmost here, these round dots basically belongs to hydrogen. So as you can see here, AN and ADN-based propellant offers a higher ideal ISP than hydrogen, while HTP on the rightmost side here, the ISP is noticeably lower. And when it comes to combustion temperature, let's look at the red symbols. AN and ADN propellants reach over 2000 Kelvin, or significantly hotter than hydrogen, which sits at around 1200 Kelvin. And this high temperature can make it challenging to use current decomposition catalysts with these new propellants. This is going to be the issue we will also address later in the presentation. On the other hand, HTP has a flame temperature that's similar to hydrogen, and making it easier to work with in that regard. When evaluating propellant performance, several factors come into play beyond just specific impulse and flame temperature. These include density, vapor pressure, and freezing temperature. In this comparison, AN-based free monopropellants stand out with higher density, lower freezing temperatures, and lower vapor pressures, along with a respectable specific impulse compared to hydrogen and other free monopropellants. For example, AN's specific impulse can reach around 257 seconds in vacuum, which is competitive with hydrogen. However, what really sets AN apart is its density, around 1.83 grams per cubic centimeter. Significantly higher than hydrogen, this higher density allows more propellant to be stored in a limited space, which is especially valuable in compact systems. The advantage and superior performance of AN-based monopropellants have been proven in orbit through two demonstration missions: NASA's Green Propellant Infusion Mission, or GPIM, and Japan's Green Propellant Reaction Control System on the RAPIDS-1 satellite. The GPM test showcased HAN's potential with a 50% improvement in feed efficiency compared to hydrogen. Together, these missions highlight not only HAN's performance benefit, but also its reliability and suitability for long-duration space missions. With the encouraging results of HAN-based propellants, there are also discussions on using HAN for a lunar mission to propel a 6U satellite that will investigate the moon's poles for water ice. Another exciting application of HAN-based propellants involves multi-mode propulsion, where a single propellant can serve different roles in the same mission. There are different approaches to make it in this multi-mode concept. One approach is to combine a chemical thruster and an electric thruster, like a liquid pulse plasma thruster in propulsion system, while sharing the same propellant. Another design involves using HAN-based system operating in chemical mode for high delta V maneuvers and switch to an electric mode such as pulse plasma for low thrust and high ISP operations. And the way to do it is switch the power supply between DC and pulse power. This flexibility enhances the system's versatility for complex missions. So, given promising results in the literature and some inspiring new concepts, we were motivated to spend the past few years developing technologies to tackle the challenges associated with HAN, especially in terms of synthesis, decomposition, and combustion. Now, let's start with HAN synthesis. Producing propellant-grade HAN solution is essential, and although low concentration HAN is commercially available in some countries, it requires further purification to remove the stabilizers and increase its concentration for propellant use. But unfortunately, we don't have access to commercial HAN solution here in Taiwan, so we had to start from scratch. In our lab, we have developed a titration process to produce high concentration HAN solutions up to 95%. The process begins with titrating nitric acid into hydroxyl amide at low temperatures to form HAN. Maintaining the temperature is critical since stack reactions occur instead of forming HAN as the temperature is too high. After getting the low concentration HAN solutions, we concentrate the resulting solution using a rotary evaporator. To ensure quality of our HAN products, we conduct FEIR API analysis, which confirm the success of our approach. Building on these methods, we have also scaled up our production. In our new system, we can now produce over 1 liter of HAN per batch. We also assess the quality of water contents of our HAN solution using thermal gravimetry. Additionally, by taking this data and also accompanied with employing a density meter, we establish a correlation between concentration and density. Our results align closely with values reported in the literature, further verifying the successfulness of our approach. So, building on our foundational work in producing high purity HAN solutions, our first challenge was to identify a suitable high temperature catalyst that can be used for further propulsion systems. This catalyst, as we mentioned, needs to be effective on decomposing HAN while withstanding the high temperature environment. That's non-typical for traditional hydrogen catalysts. Thermocatalytic decomposition is actually the typical initial method for liquid motor propellant in space thrusters. In this process, the catalyst is preheated to a temperature that allows for rapid conversion of liquid motor propellant into gas-phase intermediate product as it flows through the catalyst bed. This decomposition product then combusts further in the downstream thrust chamber then through the nozzle to produce thrust. While platinum and iridium-based catalysts commonly used for hydrogen are also effective for Han, the durability of these normal metal catalysts is a concern due to the significantly higher flame temperature of Han, as well as the acidity of the propellant. As a result, investigation into new high-temperature catalysts is necessary to ensure the reliable performance of Han-based propulsion systems. And among all these different catalysts, we consider two main types of high-temperature catalysts, the CeCO26-based and HESO aluminates. While CeCO26 offers robust structural integrity and its catalytic performance, but its catalytic performance is lower than that of iridium-based catalysts, based on what's being reported in the literature. So we chose HESO aluminate for their proven effectiveness in high-temperature catalytic combustion application and their versatility. A little bit background on HESO aluminates. HESO aluminates are a type of aluminate compound with a unique layered structure. They have alternating layers of highly packed oxide ions and mirror planes. And their general formula is ABXAL12-X019. In this formula, A is a cation in the mirror plane, and B is typically a transition or normal metal that can be replaced. They can replace aluminum in the structure. By adding different metals, we can adjust the properties of HESO aluminates to suit our needs. These materials are incredibly stable, even at temperatures over 1600 degrees Celsius. And they resist thermal shock and sintering. Thanks to our collaborators at ITRI in Taiwan and Kongshu University in Korea, we have tested several types of HESO aluminates, labeled IT0 to IT6 and KN0 to KN1, to see how well they work for decomposition. Decomposition performance tests were conducted using a high-pressure batch reactor. For each test, 1 milliliter of propellant along with 0.3 grams of catalyst were placed in the reactor's crucible. The sample was heated by a heating block at the bottom of the reactor at a rate of 10 degrees Celsius per minute. Temperature in both the liquid and gas phases, along with vessel's pressure, were recorded throughout the process. From the pressure and temperature data, we can derive several performance indicators by calculating the change in temperature and pressure. These indicators including decomposition on set temperature, reaction rate, pressure rise or gas generation rate, and burn rate. Initial screening tests using Han-acquired solution highlight the significance of catalyst support, platinum loading, and the addition of slow time. These factors are crucial for boosting catalytic performance and enhancing material robustness. Our test shows that all HESO aluminate catalysts are actually effective on lowering the decomposition temperature. Notably, the IT6 catalyst, a commercial gamma alumina pellet coated with HESO aluminates, can achieve a reduction of the decomposition over 100 degrees Celsius. High concentration of platinum impregnation improves consistency in catalytic performance, although this approach comes with substantial costs. So, in the later test, we will actually focus on this IT series catalyst. And the result also highlight the promising performance of HESO aluminum catalysts on the Han-based propellant blend SHP-163, which uses methanol as the fuel. Achieving a reduction in decomposition, these HESO aluminates can achieve reduction in decomposition temperature by about 60 degrees Celsius. Notably, under catalytic decomposition, the induction time, reaction rate, and also linear burn rates, gas generation rates, all shows much less pressure dependency compared to pure thermal decomposition, which are the red symbols in this chart. These findings demonstrate the strong potential of hexyl alumina catalysts for improving decomposition process of Han-based propellants. So, due on these fundamental research results, we actually built a 100 millinewton prototype to test the performance of these hexyl alumina catalysts on a prototype truss systems. In this initial test, propellant was supplied using a syringe pump, and hexyl aluminum pellets were used as the catalyst bed in the thruster. Successful pressure buildup in the truss chamber was achieved, but you can see here the pressure has been kept. This is due to the pressure relief. We should have a relief valve on the system, so this is actually due to the pressure rise higher than the pressure that we set on the relief valve in the current setup. So address this and to make a more comprehensive study, we are working on an improved test rig which will use a blown down propellant feed system. And this is actually our work and the work in progress. So basically, this concludes what we have been doing on the catalytic decomposition for Han-based propellants. And the next section, I will discuss the electrolytic decomposition of Han. This is quite interesting because Han is what we call an ionic liquid. So it can be decomposed through electrolysis. Various work in the literature have demonstrated successful decomposition and even quick ignition of Han-based propellant using this approach. However, there is ongoing debates about whether electrochemical reactions play a critical role in this process, or if it is primarily involved thermal decomposition due to Joule's heating as current flows through the ionic liquid. To gain insights into this mechanism, we have designed experiments specifically aimed at exploring this aspect. So we perform electrolytic decomposition tests in the high pressure chamber with side windows, so that the process can be observed and recorded using a high-speed camera. And care has been taken to avoid any voltage hysteresis during the test, as this could affect our measurements. Typically, there is about a 50 millisecond rise time for the voltage to reach the set point when most power supplies was switched on. And this can introduce some uncertainty in the electrolysis measurement, and we actually make effort to avoid this. So what we have been doing is that we load the power supply with a resistor and then switch the current flow from the resistor to the ionic liquid at the start of the test. And as you can see here, this allows us to maintain a constant voltage right from the beginning, so avoiding the voltage hysteresis, and which may contaminate our measurement. And what I'm going to show you here is actually the electrolysis procedure on a Han-required solution. So in this high-speed video, we can observe the electrolytic decomposition process of a required solution. And cathode is positioned on the left, while anode is on the right. And if we break down the video, almost right from the beginning, we can see large number of bubbles forming on the anode side. And initially, these bubbles are transparent, and this actually suggests that they are likely oxygen from water electrolysis. Shortly after that, thick brown smoke appear near the anode, which indicate the generation of nitrogen oxide. At about 0.6 seconds into the process, we start to see stratification in the liquid phase, possibly due to the formation of different liquid products. Interestingly, the decomposition reaction becomes self-sustaining, continuing even after we turn off the voltage. So for this test, we actually turn off the voltage at 3 seconds after the start of the experiment, but we observe continuous reaction after that. And our measurements show that temperature in both the liquid and gas phase during electrolytic decomposition was significantly lower than the set temperature of thermal decomposition. Additionally, we observed that the timing of the brownish smoke that we just showed in the previous slide, the timing of the appearance varied with time concentration, highlighting the role of ion transfer in the process. These findings suggest that the mechanism of electrolytic decomposition is likely quite different from thermal decomposition. The temperature data also reveal that self-sustained decomposition continues even after the voltage, which is consistent with our visualization. So you can see that this yellow region here is where voltage has been applied, and after that, the voltage has been turned off. And we also observe a go and no-go threshold for electrolytic decomposition and an electrolysis duration between 0.5 and 0.75 seconds, which means that if we just apply the voltage for 0.5 seconds, there will be a no-go. Okay, it will be a no-go. And if we slightly increase the electrolysis duration up to 0.75 seconds, then it's going to be a go scenario. And despite only a small difference on the deposited energy between these cases, this suggests that an electrochemical reaction pathway may be activated within the ionic liquid with this slightly longer electrolysis duration case. And we also analyzed the liquid residue from both the no-go and go cases, and we found that water contents was reduced in the no-go case. Here in this 3,500 wave number area is where water shows up in the FTIR spectrum, confirming that the initial step in electrolytic decomposition is water electrolysis. And for the go case, the liquid product is identified as nitric acid, which is known to be a key intermediate in hand decomposition. We further examined the initial current behavior in the process and compared it with high-speed video observations. We found that the initial rise in current coincide with bubble formation on the anode as ion migrate toward the electrode. As ion concentration near the electrode reached saturation, the current peaked and then began decrease. We observed short drop and fluctuations in current due to the intense bubbling, which intermittently blocked the flow. In the case of a 5-second electrolysis, the current has already dropped to a very low level, even before the voltage was switched off. So, based on our results and recent findings in the literature, here we propose a mechanism for the electrolytic decomposition of hand. So let's look at the cartoon on the left and on the right. When voltage is applied across the electrodes, water electrolysis initiates as based on what we have observed, which we have just shown you on the previous slides. And the electrolysis of water produces oxygen on the anodes and hydrogen on the cathode. Simultaneously, nitride ions migrate toward the anodes, where they form nitric acid, and that's why we see stratification in the liquid phase on the anode side. And hydroxyl ammonia ions are driven to the cathode, where they are reduced to hydroxyl amide. This results in high concentrations of nitric oxide near the nitric acid near the anode, and hydroxyl amide near the cathode. This nitric acid is known to have an autocatalytic effect on Han decomposition. This explains the intense brownish smoke observed around the anode. So, with this smoke, we have actually validated the electrolytic decomposition of Han is indeed initiated by electrochemical process. So let's move on to the last topic. The final topic I would like to discuss today is the separation of burn rate surge by gelling Han with fume sleep. The chart shows the burn rate chart shown on this slide. You can see that there is an order of magnitude increase burn rate as the pressure is rise from 1 MPa to 2 MPa. There is a huge burn rate jump, almost 2 orders of magnitude. And this behavior is actually undesirable for propellants, since it could lead to a reaction runaway and posing a hazard to propulsion system. But unfortunately, this pressure area, as I've been encircled using this red rectangular, is exactly the pressure range that a space propulsion system is walking around. The reason to get this type of pressure surge is due to the difference between water boiling point and the decomposition temperature of Han. At lower pressure, the boiling point of water is below the decomposition temperature of Han. Water boiling temperature at atmosphere, as you know, is around 100 degrees Celsius. And decomposition temperature of Han is around 160 to 190 degrees Celsius. So this means that the heat released from Han decomposition is absorbed by the water's latent heat. This results in a slower reaction. But as pressure increases, the boiling temperature of water rises. Once it exceeds the decomposition temperature, then decompose directly into gas product. So this will significantly accelerate the reaction rate, as you can see on the left movie on this slide. So to mitigate this, we come up with an idea of gelling the Han using fume silicon, and then we perform strain burner tests. So in this video here, we will actually play it in sync. You can see that on the leftmost test is the strain burner test performed under atmospheric pressure. And on the rightmost video, it is under 5.1 MPa, 50 bar. And well, actually, you can see that as pressure rise, the reaction propagation rate is still increased. And interestingly, on the leftmost video here, the reaction under atmospheric pressure, we can see a very slow propagation of this reaction. And it is actually so slow that I need to call it because it may take around like 1 minute to get the video to finish. And for your information, all these tests are under argon gas and argon conditions, so there is no gas-phase reaction between the environment gas and propellant. So we put together all these data points, and the first thing we found is that this pressure surge for the liquid form Han has been mitigated. Okay, look at these solid triangles. These are the points when we gel these Han solutions. So we find that the Furthermore, we also find that self-sustained propagation can be extended down to atmospheric pressure by Jiaoling Han solution, while the reaction is not self-sustainable below 0.5 MPa in liquid form. And we are actually still working on reviewing the mechanism behind the findings, why we are able to mitigate the reaction rate surge and also extend the limits of the self-propagating limit of Han solutions by joining it. But preliminary analysis show that thermal transport enhanced by fumed silica particles may be the driver for the phenomenon. With the small specific heat and size of fumed silica particles can easily be heated up and then convected to the unreacted liquid Han, resulting in better thermal feedback between the reaction zone and unburned region. The local hotspots generated by this high temperature fumed silica make decomposition of Han easier in these sites, which mitigate the pressure surge and extend the self-sustainable limits. And this is, the reasoning that we are proposing. All right. So I guess my time is almost up, and this is the summary of my presentation today. And I guess I'm not going to go through it point by point again. But in conclusion, I would like to point out that our studies confirm the potential of pencil aluminates and also electrolytic decomposition, and then we find a way to mitigate the pressure surge. And we actually think that these findings have the way for more controlled and efficient Han-based propellant systems and contributes to both the fundamental understanding and practical applications of these new technologies of Han-based propellants. So finally, I want to thank you all for your attention and interest. And at this time, I'm happy to take a few questions you may have. Thank you.
Thank you, Professor. So, do we have any questions from the participants? Any questions from the participants?
Hello?
So,
Can you hear me?
So, Professor, I think we don't have any questions from the participants right now. No questions from the participants. Am I audible, Professor?
I'm sorry, the connection is not that. Can you? I cannot hear you clearly.
Am I audible, Professor? Mic is on. Professor, can you hear us? Professor, are we audible to you? Professor, are we audible?
Or if you, or you can just type your questions using the meeting chat, and I can answer. I guess that could be easier.
Sir, am I audible to you right now?
Okay, thank you. So if there is no question, thanks for having me, and I will lead the presentation.
Thank you, Professor. So next we have Professor Satya Chakravarthy.
काफी कार्ड दो इसका वाला डाटा हटा दो आगे बोलिए ना हाँ ठीक है फॉर्मेट ना इसको ना आगे जाओ आगे का जो वाला डाटा है वाला कार्ड यार मुझे तुम भी आई था ध्यान से
Professor, are we audible to you? Professor, are you audible to you? Am I audible?
Am I audible?
Sir, I can hear you. Can you hear me?
Sorry, repeat that.
Am I audible to you, Professor?
I'm not able to hear you very clearly. Yes, please.
Sir, we will rejoin in another 1 minute. Sir, just a minute, we are restarting the review. Sir, already Sir, am I audible to you now? So, we are honored to introduce Professor Satya Chakravarthy. a professor of aerospace engineering at Indian Institute of Technology, Madras. Professor Chakravarthy is a distinguished leader in the field of propulsion and combustion with a remarkable academic and professional journey. He holds a bachelor degree from IIT Madras and master's degree and PhD from Georgia Institute of Technology. He currently leads the National Center for Combustion Research and Development, that is NCCRD, and the DRDO Center for Propulsion Technology at IIT Madras. Professor Chakravarthy's contribution extends beyond academia as a visionary entrepreneur. He is the founder of the E-Plan company, which develops hybrid aerial vehicles, and a director of a startup like Agni-Cool Cosmos, Aerovistroville, X2 Fuels and Energy, and Turu Hyperloop. He is also an advisor to Galaxy I and New Trans. His accolades include the HAL Prize, Young Engineer Award, and the DRDO Academic Excellence Award. Professor Chakravarthy's influence also spans digital learning with numerous lectures and TEDx talks available online. Please join me in welcoming Professor Satya Chakravarthy.
Thank you so much.
Welcome, Professor.
For the introduction. Let me just this is coming out of recent work that we have been doing on our research in combustion instability. This is done by one of my latest PhD students, Vikram Ramanan. So I'm actually pleased to work this particular work. It's actually a part of the PhD work. The title is Spatiotemporal Pattern Analysis of Transition and Unstable Combustion in a Small Combustor. So the whole motivation here is combustion dynamics is actually a complex process involving flame, flow and acoustic variables. The acoustics is dominated by the flame and modulates the flow as well as the flame in turn, which leads to an instability. And considering this complexity, each of these processes is complex by itself and their interaction is even more complex. Several approaches have been taken to tackle the various aspects of combustion instability. Combustion dynamics actually relates to generation of presence of good order in the context of turbulent combustors. As the acoustics resonates with the combustor, everything actually becomes more orderly when compared what would otherwise be completely turbulent. The advent of non-intrusive diagnostics and application of data analysis as a common thread to how combustion instability can be tackled. The way we will go through this presentation is we will first describe the experiments and the expected unstable characteristics, first of all. We will go through a combustor characterization through multitude of states, frequency, time domain, and joint approach. Then we will actually branch off looking at how combustion is looked at versus unstable combustion on dynamical states. The stable combustion actually has three anomalies during this condition, and in the pressure values as well as how well to mark them. And in the fixed point dynamical states, we will actually see frequency locking between flame emission and pressure, basis for a simple probabilistic model. Ultimately, the pressure and emission actually hold key to the unstable combustion. We will actually look at flame patterns in unstable condition and do the Hilbert transform. And with these, we can see that flame curves and then there is a rotation. Flame skews correspondingly in the pressure. And with this, we will actually be building time resolved images from sparsely sampled data. The combustor that we are looking at is actually a swirl combustor. We have a settling chamber through which the air enters and gets into the combustor. The combustor has a total length of about 1 to 2 meters. There is an inlet section and a unit of optical access module where the fuel injection happens, so that we will actually be able to pre-mix the mixture. As we enter the combustor, there is a swirl that induces the swirl, while the test section actually has an optical access for us to be able to image the flame in a hands-free manner with a group of PMTs, photometric, as well as a speed camera. And then we actually get into the extension ducts, which will provide the frequency, the natural frequency required for the particular combustor to interact with the flame and the swirl. And we have pressure transducers across the different locations of the duct so that we can measure what is the acoustic mode that the actually takes. From this, we actually can measure pressure, as I said, at the combustor, for example, under section, and different kinds of patterns. The stable combustion is something which has fairly low amplitude, under plus or minus 100 pascals, but you can see stray explosion from there with spikes outside of this plus or minus 100 pascal range. Whereas when you now get into a stable combustion regime, the pressure actually gets more or less uniformly to plus or minus 1000 pascals. So we want to basically first of all understand whether there is an acoustic mode in operation or not. And for that reason, we actually use the pressure data that's been obtained about 4 points. You can see one at the inlet optical axis module, one at the test section, one in the middle of the extinct ducts, and one at the exit. So with these experimental data, we are in a position to actually solve the equations of acoustics and compare the acoustic data and the theoretical expression to find out what is the full acoustic mode everywhere in the combustor based on the data that's actually sampled only in certain locations. This is a fairly standard approach based on which we are able to see that the combustor is actually exerting a closed open condition. It's a pressure maximum at the swirler and the pressure minimum at the exit. So it's kind of like whatever you do. And that's the kind of acoustics that must have exit. How we characterize the combustor is to measure the pressure and the integrated flame CH star chemiluminescence using the photomultiplier tube. We then do multiple analysis, or we actually do the encoding the time series of the measured quantities provides a direct method to understand subtle variations in the time series versus the control parameters. This is a very straightforward approach. This approach is this, a symbolic time series analysis. And symbolic time series analysis actually converts the time series into a list of symbols. And we will explain that a little bit as we go along, such that each value into a unique entity. Then we can partition these symbols by performing either a maximum entropy or partitioning or equal entropy partitioning, or equal partitioning. We will follow most the maximum entropy partitioning. And we perform partitioning absolute values of measured quantities using maximum entropy owing to the nature of the stable combustion. And the number of partitions, the cardinality of the symbolic set is determined from the variation in information entropy versus cardinality. So if here is, for example, the pressure on the left-hand side, 3 states. One is the stable combustion, one is the intermittent combustion, and the third one is unstable combustion. Throughout the rest of the talk, we will see that we are actually looking at these 2 states as we are actually talking about the approach to the layout of the presentation, the second slide. On the right-hand side, we actually see data in chemiluminescence instead of the pressure data. We're essentially looking at on one hand the pressure data and the chemiluminescence data from the flame. So the first actually how we are partitioning this data in terms of tubes such that we get an equal entropy. Means the number of partitions and the number of states will actually, the number of states in each partition should actually be such that we can get it to be equal. And then we look at the intermittent states. Based on that, we now say if you don't look at those partitions, we will find that the amplitudes are actually skewed towards one particular site and one particular state. And that is indicating that we are actually approaching a combustion instability. From what was originally equal everywhere, if you are now beginning to see the bias that is building up for one particular state, what we're essentially doing is we are now setting these thresholds under these amplitudes. Each of the thresholds is called like alpha, gamma, delta, epsilon, and so on. And we count the number of states of each of these things, alpha, beta, gamma, and so on. So we take them to be equal to the stable. But after that, when we now use those partitions, we find that this bias creeps in, and we're clearly seeing that when you now get to the unstable state, only one particular state is active, other states are being suppressed. So all the amplitudes are actually well above the last partition. Previously, the last partition was around the 85 pascals level. Now we are looking at partition amplitudes. So when compared to that is expected, the partitions are way below at the bottom. See, and the intermediate state, the last partition was at 85 pascals, and you can see multiple states that are actually peaking out when compared to no such state in the neutral combustion. So similarly, if you do the same thing for the chemical luminescence, we actually partition the states to actually get equal number of states of each partition. But then we now see this bias that is actually growing. In the case of chemical luminescence, bias is leaning to the left. When we didn't get to the unstable state, it mimics what is actually seen in the pressure. So the approach to instability for chemical luminescence shows an opposite trend at the intermittent combustion state when compared to the final state, which is equal. So very similarly, if you are able to actually do something like a wavelet transform, what we find is that we can actually do a pressure in the frequency domain, and we can see that in the case of stable combustion, you have a very sporadic set of peaks that you can get into in the frequency domain. In fact, previous actually both these what pointed out is the opposite trend of chemical luminescence and pressure during the intermittent calculations. The nature of the time domain motion is linked to the frequency domain. So let's actually look at the frequency domain is basically the motivation of from the previous slide. So if you now look at the frequency domain, the pressure oscillations actually have these peaks that are actually seen in frequency during the stable state that is spread out across the frequency range. Now, if you look at the intermittent state, it's actually peaking at a fairly low level. I mean, the amplitudes are still around 250 pascals here. So on the student, but the peak frequency, the peak amp are still at a fairly low level of about 50 pascals. This is still higher than stable combustion states. But the more thing or the interesting thing that we can understand very easily is the unstable state. When the combustion instability happens, everything, all the energy is actually packed at about the 150 Hertz mark. And there's hardly anything over here. So this actually gives you a very good sense of how this relationship exists. So if you actually look at the wavelet coherent, we find that there is all frequencies exist, and then there's a bit of a scatter that gives rise to the peak at the stable combustion, which then pipes into two for the intermittent state, and then it actually gets even more starkly varying when you now have an unstable state. So this again gives you kind of a trend on how a central peak actually splits into two, and then if you see that it's splitting into two, means it is actually going into an unstable state. So the bigger picture is that we have these kinds of tools that we are developing, previously the STSA and now the wavelet coherence, where we can see how this trend towards instability happens, so that we will be able to determine precursors to instability. If you want to do the same thing for chemical luminescence, we see a very similar picture. The peaks actually located frequently again, and fully they start shifting to the mid-frequency range in the intermittent case, and finally when you actually get to the unstable condition, you see that the peak is actually located at 150 Hertz which is the natural frequency, the quarter wave mode of the natural acoustic frequency of the duct. That's exactly the same as what we have seen in the pressure. So there is a good amount of synchronization that's happening between the chemiluminescence and the P prime in this case, which we would like explore. So is that a way by which determine some kind of like a probabilistic model of phase synchronization that will help us explain how the intermittency can be used as a picture to stability. The inherent flame oscillations are distribution of inherent frequencies. So the input flame oscillations consists of a distribution of infinite frequencies, and the intensity fluctuations are affected by the newest upstream layers, and this is essentially the basis of what we call as causality. And interaction is actually very non-local, and there is a significant memory effect. So the thermoacoustic interaction as a result of space difference between heat leak and pressure is really the integrated realm that is actually picked up at the local level and compared to the global level that what Drake had enunciated about more than a century back on combustion instability. So the onset of combustion instability is marked by identical phase difference across the flame region with the pressure oscillation. So is it possible for us to actually look at the flame and at the point there's high intensity in the flame image and correlate that with the pressure oscillations in terms of that phase is eventually the approach that we are taking. So if you now look at the stable to intermittent phase, and then let's say we actually take cases, one of them with an outflow rate of about 36.78 kg per hour, and the phase difference that we are looking at is about 1.04, and the other case is actually just a slightly higher flow rate of 40.4 kg per hour. Now these two cases, in both the cases we actually see how the transition to extinction happens. Keep in mind the axis values. We are actually starting with about, in the lower outflow rate case, which is the case 1, actually looking at the stable state having a minus 3 pascals as the pressure oscillation. We are plotting the same thing with these points that are actually kind of camouflaging the actual amplitude for the most part. But we have actually plotted at a minus 200 plus 200. Then we go into the intermittent state as we progressively decrease the phi. As the equivalence ratio is decreased, and we are getting into a more and more pure lean state, the 0.96 to 0.76 on the one hand, and then 0.95 to 0.7, we are actually getting into instability. Two states that are dependent in the first place, we actually get into the beats frequencies, and then we will actually get a full-blown instability. Full-blown instability again is not exactly a constant amplitude. It does have moments of silence as well as lower amplitudes and so on. So the beats are actually seen to not contain any other incommensurate frequencies. The frequencies are clearly shifting towards the acoustic, natural acoustic mode. So how do we actually evaluate these patterns? A little bit of an involved slides. We have to actually look at what's called the daily terms, the daily coefficients. In the interest of time and clarity, let's actually skip this and look at the actual results at some point. So how does the acoustics pull to the combustion is essentially based on the wave equation. This is a nonlinear equation that we are actually looking at, and we look at a R parameter which is equivalent to the Rayleigh index, where we look at the P and Q prime divided by the max of Q. So it's a normalized Rayleigh index, if you will. So at every iteration end, the flame oscillator has center fluctuated acoustic frequency, but with better driving and lower phase difference. However, the flow actually it tends to match only when the acoustic the instability case. Until then, you have these multiple frequencies of the flame, the flow, and the acoustics. The flame oscillator has an incentive to fluctuate at the acoustic frequency because of the acoustic feedback. That's a coupling between the acoustics and combustion that prevails weakly in the stable conditions, progressively stronger when you now get into intermittent states, and more and more intense when you now actually get into unstable condition. So if you're able to actually numerically obtain the oscillations based on this nonlinear equation that we have, we actually can mimic the way stable oscillations are, and you will clearly see, because of the nonlinearity, there are these occasional spikes that are happening even under stable conditions, but you have the intermittent oscillations in the next, and then we get into these burst oscillations, which are even more hence intermittent oscillations, and then finally we actually get into this peak oscillation for the single frequency, and this is actually leading to the full-blown instability. So if you were to actually look at the amplitude of the matches with the experimental data, we can clearly see that even under under stable states, this is actually very, very important, because we are able to actually come up with a model that explains how even stable condition can be modeled and progressively intermittent condition can be modeled, and how we can actually get all the way to the unstable condition. So the model actually predicts a particular case and the iteration as you go, pattern of the non-dimensional amplitude as you go through the iterations, whereas the case 1 and the case 2 actually has this particular variation. So we kind of see that there is a very good balance between the model and the actual experimental results. And this basically shows the phase relationship among the intensity segments, that is skip where you are actually at multiple regions that give you what is giving rise to stable oscillations versus what is giving rise to intermittent oscillations. Which part of the flame actually is triggering the instability is what we can actually see from this particular phase relationship. And when you now get to the peaks, what we showed in the previous slide is stable oscillations and intermittent oscillations. But what we are actually showing here is when we now get to the final peak-like oscillations, again, we got this region 1 that is in high correlation, and then we got these regions, we got lower correlations and so on. We are able to identify which region is creating further instabilities. So, let's actually look at the anomalous behavior during the stable oscillations itself as a precursor to the intermittence. Why is the stray anomalies that you are seeing during stable oscillations actually getting amplified to go towards the intermittent state and ultimately lead to the combustion instability is what we should actually be looking at. Right? So from our analysis on the stable combustion, we will observe that there are occasional and extremely short-lived events displaying high pressure values with other stray anomalies. The transition to combustion instability can be either through fixed point states or in a transitionary manner, which is rate controlled. So the question is, can one transition on an event-by-event basis, considering we possess a spatio-temporal feature, but it is noisy. So we have to actually look at what is the reconstruction loss that we will have corresponding to where we have a noisy spatio-temporal from the flame images. So an approach that wants a stable data rather than determining the proximity of the unstable water condition. So it's important for us to actually take that, because in combustion, the engine is actually stable. We have to know when we will become unstable. So, and we have to be able to know when we will become unstable, even looking at the stable data, rather than letting the instability happen. And that's what we are actually trying to do with this. So, we have three very different parts. Here we have the fuel is actually varied, keeping the air constant, and there are two such variations with different air values. The other one is air is actually vary with the fuel constant, and we do this at two different variations for two fixed values of fuel. So we then have put this, we have this transition unsteady pressure. So you can clearly see that there is a lower amplitude in the beginning for the case 1, and the case 2 is actually a higher fuel, so therefore, higher air flow rate value, beg your pardon, and then we are varying the fuel flow rate within approximately the same range. So the higher air flow rate value in case 2 relates to a slightly higher stable state amplitudes, and then a transition to approximately the same amplitudes of instability in the second case 1. And in the case of the case 3, we don't really have too much of a transition, but in the case 4, we actually see this transition. So we can then identify what are the signals, the pressure signals for pre-transition and the post-transition. We can clearly see there are multiple frequencies that are available in the pre-transition, and they actually converts into more or less single frequencies. We can't say again there's a noisy turbulent regime, we have the beats as well. So multiple smaller frequencies are actually, and we are getting a more organized pattern, relatively speaking, in the post-transition regime. This is captured better in a Wegener transform. And to time frequency, to plot the amplitudes, we can clearly see as the time progresses like within a course of 6 seconds. We can clearly see very intense frequency, intense tube are actually coming up at the the natural frequency of the acoustic. So how do we actually correlate these in order to get the pressure and the temp to correlate? What we find is that in all the cases, actually, there is an excellent fit between the pressure and this one, what we call experimental normal distribution and the experimental distribution. And therefore, it is actually good to go for us to be able to understand what happens within stable state. So, is it possible for us to add features to the and by doing a image processing analysis and try to look at features that will correlate to the anomalies in the first place that can then lead to intermittency and then instability. To the intensity fluctuation value that you are able to see. If you are seeing the deviation, that again is like a precursor to instability. Right? Now the question is, how do we actually get the sensitivity to of this to the intensity fluctuations is what is plotted here. I think that's a little bit of a extra work than the main theme of the thesis. So I think that's for, let's say, the paper reviewers to be happy with what we have done. We'll skip that and then get to, particularly in the interest of time, and we will get to the unstable combustion flame patterns, where we actually perform a Hilbert transform into the flame images, and then actually we collect pixels that are within about 3 degrees to obtain the brightest regions and label them as coherent image phase. So it's essentially looking at the phase difference of fluctuations of every particular pattern. So the images that we see are like this to begin with. If you now see the bottom left is actually a time-resolved image of the chemiluminescence. We can see the development of the central toroidal recirculation zone in terms of the chemiluminescence, which progressively goes and sheds. So you go from 1 to 4 below and then 5 to 6 in the next column. You can see that central toroidal recirculation zone sheds in unstable conditions, and then new toroid is actually being formed. So this toroidal recirculation zone actually has a rotational feature in it, and corresponding to this situation, as we have seen the organized way, we have a slight blip over there, as you can see, and this is expanded into one particular cycle. Although it looks like we are actually picking one particular cycle and therefore it's an anecdotal sort of analysis, we can see that that particular blip is actually recurring in pretty much every cycle after a cycle. So we can statisticize the idea that we are actually looking at as opposed to just looking at it as an anecdotal feature in one particular cycle. And when we now do the coherent image phase, we basically then get on, so we actually superpose the coherent image phase contours on top of the images itself over here, and we find that the flame actually is coherent within plus or minus 3 degrees as a tolerance in these particular areas, which means that these are all oscillating with respect to each other in a single, more or less in a single phase, and that is what is giving rise to the existence of the instability. So if you were to then look at how the coherent image phase and the heat release oscillations from the PMT and the acoustic oscillations, all three, if you were to actually look at that, right, the coherent image phase is plotted as the dark, and then the total heat release rate is plotted next, and then the P prime is plotted. Of course, we need to have a different axis for the pressure, so that's on the right hand side. So we actually have all the three plotted, and then we try to actually look at how the phase relationship between these evolve as we go along. And we can, as we can see, as the central toroidal recirculation zone evolves, the coherent image phase is actually going further down, and then a new coherent image phase region is evolving as you go to the instant 8 when compared to the instant 1, and so on. So what is actually causing that pressure blip? Is again a very interesting thing that we actually looked at. So we are motivated to investigate why the blip is actually happening, and broadening, particularly at its maxima, which causes the asymmetry between the compression and the rarefaction phases. And such an asymmetry can be the result of more than one process. The first reasoning could be simply to say nonlinear, but we want to quantify the nonlinearity using the power by particular frequency through the nonlinearity. So we actually have a quantification of the nonlinearity, or QNLP, which is a bidivergence of two frequencies that we are actually looking at, and how does this exactly start showing up. So we now have a nonlinear power generation, the highest at the duct acoustic mode, then it's predominantly linear. Then we have significant, so the question is significant, but is it enough to cause a pressure blip is a question. So we could perform the same for the flame derived measures by considering two regions instead of just looking at the pressure alone. And so the QNLP of the flame emission space time series is actually performed, and we get these results for the THRR and the UHRR and the DHRR. So we actually split them into 3 parts and look at these phase differences and get a conclusion out of qualities. The next thing that we do is to actually look at, as I mentioned, there is a rotational symmetry that actually happens in the toroidal recirculation zone that the flame exhibits by itself. Is there a way by which I can identify the rotational symmetry using a computer vision algorithm called SIFT algorithm? And that's what we will actually be doing over here. Now, when I try to apply the SIFT algorithm, it's a fairly well-established algorithm in computer vision, where we actually can locate where that rotation happens. So the rotational symmetry is actually marked by the conducting flame branch predominantly, And when we evaluated for the crop region near the flame holder, we observed that this centers associated with the flame curl near the flame holder. And this curling is actually which is marked by the red crosses, as you can see. And the predominant centers correspond to either the center line of the curling branch, as you can see how the green crosses actually get convected further and further. And then the next cycle of green crosses starts convecting further and further as we saw, as we see. So what we find is that when you now have a stable flame, there is no rotational symmetry observed. The rotational symmetry actually evolves through the intermittent process and ultimately gets to the stable state, unstable state. So what is the correlation between the centers of rotational symmetry and the pressure blip is essentially the question, because we were trying to use the QNLP as a marker for nonlinearity in the pressure data. And what we find is that if you now look at the wave bottom, right, and then look at the fixed width, right, at the highest maximum, you will find that detected upstream vortex centers actually keep growing as we go along, and that actually relates to the blip. So every time you have these instances of rotational symmetry appear, you actually have a flame blip. So the pressure blip is actually very well correlated then with the flame data itself. So from there we can actually look at what are the flame modes and how can we reconstruct from the sparse data. I think this is probably one of the last slides coming close to the conclusion. Or maybe you should just skip this and get directly to the data here. So the mode 1 here actually displays the axisymmetric flame branch that convects following the merger of the individual flame branches. And the mode 2 is actually made of two regions, the curling flame branch near the flame holder and the flare downstream, which is the red boxes that you are actually seeing in the images here. So that's essentially coming from the image analysis that we have done in the previous slide. So if you now were to actually look at temporal evolution of these different flame modes, the mode 2 near the flame holder versus the mode 1 that is actually getting conducted further out with the pressure data, they play out like this. So we actually have to look at which one is skewed over the other and causing that pressure blip, and that's what this particular thing presents. So in summary, combustion dynamics is actually a development of ordered phenomenon from a disorderly turbulent state, which can be studied in experiments from time and frequency domain methods. So what we have done is to actually develop a particular sensor that can be put even in engines, practical engines, to be able to study the time-dependent chemiluminescence data. So the stable state is characterized by the presence of high amplitudes which are stray in nature, with transition to instability seen to be marked by increasing phase synchronization. And the parameter variation effected in a probabilistic manner for two sets of oscillators, even for flame and pressure, is seen to qualitatively match dynamical states observed in the flames. And the strain anomalies can be picked by forming a probability distribution and using the VAE to obtain with a better match with unsteady pressure compared with intensity fluctuations. And unsteady combustion is characterized by flame branching, curling, merging, and convection. Instantaneous bright regions of the flame are seen to be better drivers of combustion stability, as we have seen from the CIP, the coherent image phase measurements. The flame blip seen during unstable combustion at the maxima is influenced by nonlinearity, but other linear processes also. And the flame branch curling is characterized by centers of rotational symmetry, with the persistence of these centers having high correlation with the persistence of the pressure blip. Thank you very much.
Thank you, Professor. So do we have any questions from the participants? Thank you so much, Professor. We don't have any questions from the participants right now.
Okay, thank you for the opportunity to.
Thank you so much, Professor.
This is.
Thank you once again to each of our keynote speakers for gracing us with their knowledge and vision. With this, we conclude our keynote session and express our sincere thanks to all our keynote speakers and attendees for making it a truly enlightening session. We now invite you all to join us for the high tea, where we can continue discussing in a more relaxed setting and foster connection over refreshments. Thank you.